Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 11, Lesson 6 on bivariate data analysis. All right, that's a fancy term, bivariate data analysis. So let's get right into it and start discussing what this is. So bi always means two, bicycle, whatever, binomial, right? Bivariate data analysis means that we're really going to be analyzing two different variables that are somehow paired up. Now, statistics contains tools to understand why there's variability in a data set. Sometimes we try to relate the variability of one variable compared to that of another when the two variables are linked through a common subject, a person, a day, a plant, whatever. And this is called bivariate data analysis. In fact, the last 4 lessons of this unit are really going to hone in, or I think it's actually 5 lessons of this lesson, are going to hone in on this particular idea. The idea that I've got two variables and I'm trying to understand perhaps the variation in one as being a product of the variation of the other. So let's take a look at our first exercise. A sample was taken of 10 low and high temperatures for a given day in Fahrenheit in the month of April to try to establish a relationship between the day's low temperature and its high temperature. All right, so let's talk about this. So, we go, it's April, whatever, wherever, and we go and we take 10 low temperatures, and again, these are paired up by the day. So in other words, on the day when it was 26 out as a low, it had a high of 51. And then there was a day where the low was 28 and the high was 50, a low of 30, a high of 57, etc. So again, whenever we have a bivariate data analysis, those data pairs have to be matched up. They both belong to the same person or the same day or whatever. Now, what we're going to be doing, right, is we're going to be now plotting, right, this data on this piece of graph paper to create what's called a dot plot or a scatter plot, a two-dimensional dot plot or just a scatter plot as it's called. Now, in order to do that, what we actually have to do is we've got to figure out how this is scaled. Very often on standardized exams, you have to decide on the scale in which to put on here, as opposed to it just being given to you. Now, let's talk realism and then we'll get into talking about the scale. In any realistic, real-world setting where you were doing this kind of analysis, you would put this data into either a calculator or into a spreadsheet program, and it would create this scatter plot for you, and you wouldn't think at all about the scale because, quite frankly, it would come up with the scale for you. All right, but we have to think about the scale. So let's take a look at our piece of graph paper really quickly. Now, without you going through all the trouble, this graph paper is a 20 by 20 grid, okay? There are 20 sort of like grid spaces here, and there are 20 grid spaces here. And it says, consider including axis breaks on both axes. What does that mean? Well, this is obviously, right here is obviously the point 0, 0. All right, but notice none of our temperatures are even remotely close to 0. So if we literally left that as 0, 0, then what would happen is all of our data would kind of be, it'd be like right around up here, right? None of it would be down here because a lot of this space would never get used. So let's first think about the low temperature, which is going to be on my x-axis. Now, the smallest low temperature is, I guess it's that 26. And the largest low temperature, conveniently enough, is that 45. So just for a second, the range in my lows, 45 to 26, is equal to 19. Now, I could fit 19 in here. I really could, because I've got 20 spaces. But I'd literally have to put the 26 right there, and the 45 would end up being the last space on there. And even though that might be okay, it wouldn't really be ideal. So what I'm going to do is I'm going to make these things go by 2 along here. I'm going to put a little axis break in, like this. And then what I think I'm going to do is I'm going to start right here, not at 26, but maybe I'll start at 20, and I'll go by 2. So 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, 50. right? And that's going to comfortably get all my data in because I need to get low values between 26 and 45 in. I can easily get that in, and it's going to take up a decent amount of that x-axis. Now, if I had to go like bigger, I could maybe space them by 5s or 10s or whatever. I don't need to do that here. I can fit them easily. Same kind of analysis for the high temperatures. The highest high temperature is that 72. The lowest high temperature is that 50. So my range in high temperatures is 22. And now I really have my hand forced. In other words, there is no way to fit 22 on here because I only have 20, right? So yet again, what I think I'm going to do is I'm going to put in a little axis break. Okay, and an axis break serves to say, hey, there's some space between the origin and my first thing. So I'm going to start at 50, and I'm going to go up by 2s. So I'm going to have 50, 52, 54, 56, 58, 60. I don't need to mark everyone, and I shouldn't mark everyone. It's just going to make it too crowded. 62, 64, 66, 68, 70. 72, 74, 76, 78, 80. And again, I don't need to mark any more off because that's enough, right? I need to just get up to 72, so 50 through 80 is going to get the job done. Now, I just need to create a scatter plot for the data on the grid, all right? And I just want to be careful when I plot it, right? I need to plot the point 26, 51. So I'll come out here to 26, and my 51 is right about there. I'll go to 28 and 50, so that's going to be right here. I'll have 30 and 57. I got to be careful here. That's right here. Hard for me to draw my boxes. 32 and 54 is going to be right here. 34 and 60, that one's actually pretty easy because they're both even. 35 and 58, that's going to be right here. 37 and 64. Oh, I'm going to make sure 64 is right here. Got to be a little careful. 38 and 66 is right here. 41 and 63 is going to be right here. Oh, it's right in the middle of a box. Let me just make sure. Yeah, that's right. And 45 and 72 is going to be right up here. All right. And again, the idea is I create these scales on my x and my y axis so the data takes up the majority of sort of the grid, right, with all the data points being able to be there, right? If I had scaled my x-axis in terms of 1s, it might spread out a little bit better. It might kind of reach into here and down into here, but we don't need to do that. Okay, let's talk about letter C. Draw a line of best fit through this data set. Now, I know you've seen lines of best fit before in earlier math classes and in science classes, but the idea now is that I take a straight edge, I bring it over to my data, and I kind of rotate the straight edge in a way, it's probably easier for you than me, rotate the straight edge in a way that it is roughly parallel with the data, and there's roughly the same number of data points above the line of best fit as there is below the line of best fit, okay? And again, eventually the calculator is going to produce the line of best fit for us, not in today's lesson, but in tomorrow's, okay? So right now we're just what we call eyeballing it, okay? We're just doing our best to get that line of best fit in. Let me draw it in red so that it stands out a little bit more. Okay. Go back to blue, and let's get rid of our ruler, which we don't need anymore. And that's a pretty good line of best fit, right? Most of the data, right, it's a pretty good balance between being above the line and being below the line, right? We don't want the line to be kind of like in some weird way, like cutting through it so that it's not parallel to the data, our line of best fit. All right, now let's take a look at letter D. Calculate the slope of the line you drew by picking off 2 points off the line, not necessarily data points. Round your slope to the nearest hundredth if needed. Okay, well, we know how to calculate the slope of a line, right? If we've got 2 points on the line, we can just do the change in y over the change in x. Now granted, I managed to draw this line right through that particular point, but I'm going to ignore that for right now. I'm going to look along this line and I'm going to try to find 2 points that it goes through that are very obvious. Now your 2 points might be different if, obviously you had a different line of best fit drawn. But right now I can see that this thing goes through the point 30, 54. So I'm going to write down that point. And it goes through the point, this one is 40, 66. Right? Now again, you might choose 2 different points. You just got to find 2 that you can definitively say lie on that line of best fit. And once you have it, you can calculate the slope. Remember, the slope will always be the difference in the y coordinates divided by the difference in the x coordinates. Oh, that's going to work out nice because my x's are 40 and 30. Anyway, that's going to be 12 in the numerator, 10 in the denominator, and when I divide it, it's going to be 1.2. Again, I didn't need to round mine at all, and it actually says round to the nearest hundredth. If needed, I don't need to round mine to the nearest hundredth. And again, I just got lucky. Like literally, I just drew the line of best fit, and the 2 points I pulled off were different by 10 units, so that made this division work out very nicely. So my slope is 1.2, all right? Let's talk about letter E and maybe get rid of this ruler so it's not so distracting for us. Let's take a look at letter E. How can you interpret the value of the slope in the context of this problem? Use appropriate units. Well, I'd like you to think about this a little bit. We certainly have talked about interpreting slopes in like applied linear problems before. I know it was a little while ago, but see if you can tell me what that slope really means. Well, keep in mind what we really have, right? The slope in this case was really the change in the high temperature divided by the change in the low temperature, right? And I can really think about that as being 1.2 degrees Fahrenheit per 1 degree Fahrenheit, right? It's a good way to think about it, right? So what this really tells me is that for every 1 degree Fahrenheit that my low temperature increases, my high temperature increases by 1.2 degrees Fahrenheit. For every 1 degree Fahrenheit, our low temp goes up, the high temp goes up by 1.2 degrees Fahrenheit. Now, you very likely will have a different answer because in theory, you've drawn a different line of best fit and you've pulled 2 different points off of it, so your slope should be slightly different. Now, don't get me wrong. Your slope should be slightly different. I would say any slope between maybe 1 to 1.5, you should feel comfortable with. If you've got a slope that's less than 1 or let's say bigger than 2, you've done something wrong. Something has gone wrong, okay? But your interpretation would be different. If you got a slope of 1.5, then you would say for every 1 degree Fahrenheit, the low temperature went up, the high temperature went up by 1.5 degrees Fahrenheit. Something like that. Okay, let's take a look at the final piece here. Letter F. Would you characterize the relationship between the low and high temperatures as a positive correlation or a negative correlation? Explain. All right, well, let's go back to the graph for a second. Would you consider this a positive correlation or a negative correlation? What does that mean? Pause the video now and see if you can remember learning about this in a previous math course. All right, well, what it basically boils down to is, do the 2 variables move in the same direction? In other words, as one variable gets larger, does the other variable get larger? If so, it's a positive correlation. Or as one variable gets larger, does the other variable get smaller? In which case, it's a negative correlation. In this case, obviously, as the low temperature is getting higher, the high temperature is also getting higher. That makes all the sense in the world, right? So this is a positive correlation, because as one variable gets larger, the other does as well. Right? And there are many, many circumstances that as one variable gets larger, the other variable gets smaller. It might still be a very strong correlation, but it would then be a negative correlation because they're sort of moving in these opposite directions of each other. Let's play around a little bit more with that idea in the next exercise. Two variables can have a strong relationship with one another known as a correlation, but might not have a causal relationship. A causal relationship exists when the change in one variable literally causes the change in the other variable. All right? And again, you can have situations where two variables sort of move in lockstep. One of them gets larger, the other one gets larger, or one of them gets smaller and the other one gets larger if it's a negative correlation, but they are not causing each other to change. All right? That's a correlation, but not a causation. Okay, so let's take a look at that in exercise 2. This is something that you will always be asked about on standardized exams, the difference between two variables being correlated versus causative, one causing the other one to change. Let's take a look at exercise 2. In each of the following scenarios, two variables are given that, if plotted, would have a strong correlation. In other words, a scatter plot where the data falls nearly in a line. Do two things. One, state whether you think the correlation would be positive or negative. And two, determine if there exists a causal relationship between the two variables. Okay, so I'm telling you, in each one of these things, if we could draw a scatter plot, we would get data that fell pretty much on a line, like in our first exercise, okay? The question is, would it be a line that has a positive slope or a negative slope? And then, would it be a situation where one variable is causing the change in the other variable? Let's take a look at letter A. The high temperature in New York City and the number of bottles of water sold. Okay, so would that be a positive correlation or a negative? And so what you want to say to yourself is, if I increase the high temperature in New York City, will I increase the number of bottles of water sold, or will I decrease the number of bottles of water sold? So that's the first question. And then, is the increase in the high temperature in New York City causing either the increase or decrease in the number of bottles of water sold? So pause the video now and see if you can answer those two questions. All right, well, this is definitely a positive correlation. All right, definitely positive. So as the temperature goes up, the number of water bottles goes up, right? And it's also a causal relationship, right? Yeah, causal, not a casual, a causal relationship, right? And it's a causal relationship because simply, I can't make that stay red no matter what I do. Simply because when it gets hotter outside, people get more thirsty and buy more water. It's that simple. If you were to be in New York City on a day where it was 40 degrees Fahrenheit as its high, you wouldn't find a lot of people buying bottles of water. You know, there'd still be people buying bottles of water. But then if you were in New York City on a sweltering 95-degree day, you'd see the number of bottles of water just skyrocket because people are more thirsty, right? The temperature change is causing the change in the number of bottles of water. So there's a causal relationship. Let's take a look at letter B. A person's height and a person's shoe size. Okay, great, right? Again, I want you to think about it. As a person gets taller, does their shoe size get taller, in which case, larger, in which case it's a positive correlation? Or as a person gets taller, does their shoe size generally get smaller, in which case it's a negative correlation, right? And then, is a person getting taller, or is, a height of a person causing whatever the shoe size is? So pause the video now and see if you can answer those two. All right, well, again, it's another positive relationship, right? As the height increases, the shoe size will generally increase, right? So in other words, if you have somebody who's 5 feet tall, they're going to have a smaller shoe size generally than somebody who's, let's say, 7 feet tall. Seriously, I think Shaquille O'Neal wears size like 18 shoes or something. I, standing at 6 foot tall, only wear size 11 shoes. Okay, so again, positive correlation. As height goes up, so does shoe size. But this no longer is a causal relationship. It's not causal, right? A person's height is not causing their feet to be larger. That's not the way it works, okay? So it's not causal, even though there's a correlation. Let's take a look at letter C. A person's weight and the amount of time they spend exercising per week. All right, well, I've already walked you through a bunch of these. Think about that one. Okay, now this one's negative, right? And really, it's negative this time if we think about it this way, right? As the time spent goes up, right, the person's weight is going to go down, right, because they're going to lose weight, right? If I spend almost no time in the gym, my weight's going to go up. If I spend a lot of time in the gym, right, getting on a treadmill or whatever, my weight's going to go down. So this is a negative correlation, and it is definitely, I keep wanting to say casual, it is definitely causal, right? There's causation there. The amount of time that I spend in the gym is causing the weight to go down. All right, and the final one, which I think is a little bit tricky, but let's take a look at letter D. The number of texts sent per day and the dollar amount of savings for retirement. Okay, so what do you think? Negative or positive, right? And causal or not causal? Pause the video now and think about this. All right, well, this is going to be negative. Okay. Now, this one's a little bit tricky because it really has almost nothing to do with either one of these. It has to do with the age of a person, right? So the older a person is, the more they have saved for retirement and the less number of texts they tend to send per day. Older people tend to send less texts per day than younger people, right? So as the amount of savings go up, the amount of texts go down. But this isn't causal, right? It's not causal. It's not that the amount of savings is causing the number of texts to go down, and it's not that the number of texts going up is causing the amount of savings to go down, right? It just happens to be that young people, right, send a lot of texts but have low savings, and old people tend to send very few texts but have quite a bit of savings. All right, so they are nicely correlated. They just don't happen to have a causal relationship. Now, there is a statistics proverb. I'm serious. This could be inside of a fortune cookie. Correlation doesn't necessarily mean causation. In other words, you could have these two variables that are beautifully correlated. I mean, like you plot them on a scatter plot and they almost completely fall in a straight line. But that doesn't mean that one of the variables is causing the other variable to happen, right? So variables can have extremely strong correlations. I mean, really strong, but no causal relationship. This often is the case if there's a third variable that is causing the variation in both of the other two. In that last exercise with the texts and the savings, that third variable was the age of the person. This is known as a lurking variable. That is definitely top 5 in terms of mathematical terminology for me. Now, unfortunately, you don't need to know that term, but boy, if I was going to force you to memorize one, it would be that one, a lurking variable, a variable that isn't in the problem, and yet it is basically forcing the change in the two variables of the problem. So let's take a look at a classic example. The table below shows the number of firefighters required to fight a given fire versus the dollar damage done to the house by the fire. So maybe, somebody did a study, and they found, there was this one fire, 2 firefighters were there, and it caused $2,932 of damage. Then there was another fire that took 3 firefighters and it caused this much damage. Another one that took five firefighters, it caused this much damage, etc. Let's take a look at letter A. Are the data positively or negatively correlated? How can you tell? Now, I know like fire is definitely a negative thing and all of that, but that's not what the question is here. Pause the video now and tell me whether this data is positively or negatively correlated. Well, it's definitely positively correlated, right? As the number of firefighters is going up, the damage to the house is also going up. So that's always the question. Are the variables moving in the same direction? That's a positive correlation. If they're moving in opposite directions, that's a negative correlation. So this is a positive correlation. Okay. As the number of firefighters goes up, so does the dollar damage. All right, letter B. Does the number of firefighters cause the damage done to the house? If not, what is the hidden variable causing both variables to change? Okay, so let's get it right out there. No. Right, so for this, no, definitely not. Right? This is not causal. The firefighters aren't causing the damage to the house, right? So there is no causal relationship here. You know, if there was, then we would just say, hey, that house is on fire, don't send any firefighters. There'll be no damage, right? That's not it. So what is the lurking variable? What is the lurking variable? Pause the video now and see if you can write something down. Well, the lurking variable is the severity or the size of the fire, right? That's it, right? Let me use size of the fire. I'm going to put 3 exclamation points here. The lurking variable size of the fire, right? So a larger fire both does more damage and requires more firefighters to fight it. A smaller fire requires less firefighters to fight it and causes less damage. And yet, right, people often confuse causation and correlation, and they'll say, oh, well, I mean, look, you know, more firefighters, more damage. So, hey, if we don't want there to be very much damage, we just shouldn't have any firefighters go to that house. Well, that would be a disaster, right? Because then there'd be even more damage caused. So make sure that you understand this difference between correlation and causation. All right, so today we got into the first situation where we looked up at paired up variables, right? Bivariate data analysis. And what we're really seeking to do now, we're still trying to answer statistical questions, right? But now we're trying to understand the variation within one data set based on variation within another data set. Why do high temperatures vary? Maybe that's explainable by the variation in low temperatures. You know, why does the damage done to a house by a fire vary? Well, maybe that can be explained or at least understood when we look at the variation in the number of firefighters that are there to fight the fire, right? So, you know, we want to always be answering the question of why is there variation in the data, and sometimes we want to look at 2 data sets that are paired together to explain and understand that. And we're going to be doing that for the rest of this unit in a variety of different ways. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.